just not something I'm looking forward to. So.
Yeah, it's kind of dark, but it's okay. It's okay.
.30, right, Jen?
Hey, I just show up.
Was it an email that said 1:30 for this?
Everything was 1:30 except for on the web, which was done.
So all the announcements. Now we know how people get their information. Only a couple of us were here at 1 o'clock.
Well, you can see how little the 1 o'clock crowd was.
Where did it say 1 o'clock?
1 o'clock was the information that we had.
Didn't it say 1 o'clock on the poster?
And it said 1 o'clock on the Atmos page.
Yeah,
it totally said 1 on the poster.
Yeah, it said 1 on the poster.
Because that's where I got mine.
Marcel sent the committee an email.
That's where I got mine. That's where I got mine.
Yeah.
You said it out something that said 1:30?
I did, yeah. So I scheduled the room from 1 to 4, so that's
1 to 4. That was pretty optimistic.
Yeah.
Should have scheduled it from 1 to 2. Then you would have been the smart thing.
I just figured you'd be best.
Yeah. All right, thanks everybody for coming out, especially those of you here at 1 o'clock for the talk that apparently was starting at 1:30. Today's going to be the Master's Defense for Marcel Caron. Marcel's came here from the University of Maryland 2 years ago, so he's been working hard to get his master's degree finished. He's had to overcome quite a bit. First, he had to deal with the fact that his advisor was gone for 6 months while he was writing his thesis, which we spent a little bit of time on Skype trying to work on. He also had the incredible challenge of having to steal data from M.Sc in order to do this work, although we won't tell you who helped us in that theft. And I'll just make a quick comment that he's been supported by the C-STAR program working with the National Weather Service. He'll be talking today about evaluation of cool season M.Sc precipitation forecasts over the western U.S. Just a quick introduction of what to expect. Marcel will give a presentation, and then I believe we have the committee ask a question each. Is that what we're doing now still? A little bit?
Sure.
Then we'll open it up to the audience, then you'll be excused, and we'll finish up the question from there. So without further ado, Marcel.
Cool, thanks, Jim. So I just want to thank you guys for taking some time to learn about model validation. If you're interested in weather forecasting, you should be able to take something away from this. And also especially my committee for taking time to schedule this, their busy summer schedules. So just to start, this is an evaluation of M.Sc modeling systems over the western U.S. And the cool season specifically, precipitation forecasts. So just to start out, I'm gonna give you just a quick overview of what to expect from this presentation. So in chapter 1, I'll be talking about the sort of context and the background, the motivation for studying these modeling systems and in this context. In chapter 2, I'll be talking about how model evaluations are done, what questions are asked, and the methodology used to answer those questions. And chapter 3, we're going to look through some of the results of this evaluation, and chapter 4, just the summary of the findings. So before I get into that, there's a lot of value to look at the Western U.S. specifically. And first of all, industries depend on good weather forecasts, and the bad forecasts have critical implications for business, transportation, public safety. For example, a very obvious example of a business side of things is the ski industry here in Utah and across the Western U.S. And then the other thing is that complex terrain in the Western U.S. is a good way to measure how models handle complex terrain in general. And so not only does this area have a lot of complex terrain, but it's relatively populated, and so that makes it a relevant area of study. So to start, the last year had several major upgrades to critical modeling systems. So the modeling systems that we'll be looking at in this evaluation are listed up here. The HER version 2, this is the high resolution rapid refresh, which was released in 2016 operationally. Its successor, the version 3, which was released just last summer. The global forecast system version 14, which was released in 2016 as well, and its successor, the version 15.0, which was released operationally a month ago. And finally, the European Center's integrated forecast system high resolution model. This has performed very well in terms of skill in other evaluations. It's considered a highly skillful model. So that is also of interest, just to compare all the models that we're investigating. And we're particularly interested in the HER version 3 and the version GFS 15.0. These are the major upgrades that we're talking about, and how they're evaluated with respect to two groups. The first is the HER version 2 versus the HER version 3. These are considered high resolution models at 3 kilometers both, horizontal resolution. And the other 3 will also be evaluated but together because these are operated globally and are coarser models. So in summary, some of the major upgrades between the modeling systems include an upgrade in the vertical coordinate system between the HER version 2 version 3, in that the current version uses a sigma at the surface, a terrain following at the surface, and isobaric loft. And also an upgrade to the PBL scheme that was used previously and just upgraded to a new version 3.8.1. And in the GFS, there are 2 major upgrades. One particularly major. The first is a microphysics scheme was changed from the Zhao to one developed by the Geophysical Fluid Dynamics Laboratory. And also, very major is the change in the dynamical core to an FV3, or the finite volume cubed sphere spectral dynamical core. And this is expected to increase the skills substantially. So that's the motivation to look at these models, is to test how these improvements changed model skill and model bias. So how are models evaluated? We used a station-based approach, which has some precedents in previous studies that our group has made and other groups have made. So for example, Lewis et al. 2017 and last year Gowan et al. 2018. essentially we're comparing point observations with interpolated model precipitation forecasts. And we're choosing station networks that represent upper elevation locations and lower elevation locations. And I'll explain those in a later slide. But essentially in the model evaluation, we're asking two questions related to model bias and model skill. The first related to bias is under what circumstances do the models overpredict or underpredict precipitation? And with regards to skill, we're asking how well does the model capture precipitation events? And we choose certain metrics that sort of go at these questions from different angles. So for bias, we're using the bias ratio, frequency bias, and bivariate histogram, which I'll explain in the results section as we get to it. And for skill, we're using skill scores that are based on a contingency table. So the idea of a contingency table is quite simple. A forecasts an event to occur in one area, observations see, or the event actually occurs in another area, and depending on which area you are in these circles, it's considered a hit if both the model and the observations see an event, a false alarm if an event was forecasted but not observed, and a miss if it was observed but not forecasted. So these are tallied up for each event in whatever period we're looking at, and those numbers are input into equations to get our skill scores. So the three that we're looking at are the hit rate, false alarm ratio, and equitable threat score, which I'll explain in a future slide as well. So I mentioned how evaluations are performed, but we need observations in order to compare the model with the real world. So what we're using are two networks. The first is the automated surface observing system. These are considered, or we consider this our lower elevation data set, because these are located mostly at, or primarily at airports, lower elevation locations, but not exclusively, just mostly. And they measure precipitation at 0.01 inch precision. Our second data set, or our second network that we're taking data from, is the SNOTEL network. These are contain stations that are located at upper elevation locations. This is our upper elevation data set. And they measure precipitation. These stations measure precipitation at 0.1 inch precision. Both ASOS and SNOTEL stations experienced measurement errors that we know about specifically, or two that I'll highlight are undercatch of precipitation when winds are increased to a certain point. And this affects different kinds of precipitation differently. And this affects both stations. Additionally, SNOTEL sites experience an expansion and contraction of the gauge that generates a artificial diurnal cycle in the precipitation amounts. So in order to combat that, we just use 24-hour precipitation and avoid that issue entirely. And just to show you, here's the orientation of where the red sites the lower elevation data set, ASOS sites, and the blue the upper elevation SNOTEL sites. So we have our model data and our observation data and our methodology for doing the evaluation, and now we've chosen a cool season to look at, which is the 2017-2018 cool October through March season. And just to get some context for the season before we evaluate it, we looked at the climatology of October through March precipitation at SNOTEL sites and at ASOS sites, and we see that not surprisingly, the Pacific Northwest features some of the largest October through March average, 30-year average precipitation. You can, according to this, the colors on the color bar. And at lower elevation ASOS sites, it's similar, as well as some coastal sites in the Northwest. If we compare this, the precipitation in the 2017-2018 cool season with these amounts using a precipitation fraction of the climatology. So these are the lower plots, SNOTEL on the left and ASOS on the right. And on average, this cool season was about 40% below average, average across all the stations. Although there's some variations. For example, in the SNOTEL data, we see that this area here featured some close to neutral and sometimes a wet season compared to climatology. At ASOS sites, we see quite a bit of variation from station to station. There were a few, well, this is a theme that we see throughout the evaluation, is this sort of variation from site to site at lower elevation ASOS sites. And ultimately, we thought perhaps undersampling, or these sites feature are very low moisture sites, see little events, and thus some sites may have undersampled precipitation throughout just the season that we're looking at. So in order to combat that, we removed some stations that were that may have been seeing some undersampling in a conservative way. So specifically, a station needed to see 5 days each of measurable precipitation. That's 0.01 inches of precipitation over the course of the cool season at least, and over the course of the cool season at least 0.5 inches of precipitation in order to be counted. So the result is what we just saw, these red areas here. We ended up removing some stations, the especially dry site. And we found that this was a good balance between keeping some dry sites and maintaining our sampling of low moisture sites, but also removing sites that where undersampling may be a big issue. So moving on into chapter 3, the results section, I'm going to start with the HER version 2 and version 3 comparison, and we're going to start looking at bias between the models and in general at lower elevation ASOS sites. So on the left, we've got HER version 2 evaluation, HER version 3 on the right. We're looking at bias ratio. This is the ratio between total modeled precipitation over the course of the cool season and total observed precipitation over the course of the cool season. At the bottom, we show the averages among all stations. And we see that between the HER version 3 and version 2, the means are not very different at all, are essentially the same, and standard deviations are quite large. So we'll see in SNOTEL sites this is a lot smaller. This means that bias varied drastically from site to site at lower elevation ASOS sites. And then the other conclusion here is that sites seem to be slightly wet on average over the cool season. Next, we can look at the upper elevation SNOTEL sites, and we see again the means and the standard deviations, and the comparison shows that there's also not much of a difference, and these seem to be quite neutral. I should also mention that when considering bias, we established a few bounds between 0.85 and 1.2 throughout the evaluation as the range in which we consider a model to be neutral. And this is just to give the models some leeway given some measurement error in the observations. So these are considered neutral, and the standard deviation is quite low. So from site to site, bias doesn't vary as much as it does at lower elevation ASOS sites. So next, we're looking at event frequency biases. These are the, for each event size, we're looking at the ratio between the number of events that was modeled and the number of events that was observed. And we do this for each event size, and we consider again that over 1.2 is an over prediction of these types of events, and under 0.85 is an under prediction. Within the green is considered neutral. So in this case, both the HER-V2 in red and the HER-V3 in blue slightly overpredict precipitation, generally for small events, but this is not a very large overprediction and is sometimes neutral, especially for larger events, or veering towards neutral. We can look at the snowtail sites as well. We see that for most event sizes, both the HER version 2 and the version 3 tend to be closer to neutral prediction of event size, or of frequency of event, sorry. So altogether, we see that there are small differences, once again, between the versions of 2 and version 3 of the HER, and generally we're slightly wet or over-predicting events at ASOS sites, and more or less neutral at upper elevation snowtail sites. Finally, we can look at bivariate histograms. These are the frequency of, for each event, it's the frequency of occurrence of an observed and modeled event. Shown expressed as a heat map here. However, essentially, we're looking for frequent event pairs to fall along this diagonal line, this one-to-one line, and we're looking at 2 things. We're looking for the accuracy of the bias, if it generally, on average, tends along this one-to-one line, or if it's over-predicting or under-predicting precipitation in general. And we're also looking at precision, so how close together are these values. So, and we'll see that a little bit clearer in the snowtail sites, but at lower elevation ASOS sites, comparing the HER version 2 and version 3, we see they're not very different from one another. We also see that the precision is very low. The spread of these values is very large. This means that bias varies, and over prediction or under prediction varies drastically from site to site. And on average, you would say that it tends towards neutral, but that's tough to say. I'll also explain these dots. While they represent, for example, the green dots represent average modeled event size for each observed event size, and vice versa for the blue. Essentially, this is used to make it easier to see what the accuracy and what the spread is. So just comparing to snowtail sites to drive this home a little bit better. The precision is a lot higher, as you can see. Event pairs fall closer together. The spread is shown by the dots here. The blue and green lines is closer together, and the accuracy is not very bad. It's very close to the one-to-one line for both the HER-V2 and the HER version 3. So essentially, the bivariate histograms they reflect what we saw in the bias ratio results and in the frequency bias results. And on average, there's no strong over prediction or under prediction. However, there's a large variability at ASOS sites compared to variability at snowtail sites. So this was the bias evaluation of the HER version 2, version 3. Next, we're looking at skill. We're trying to understand what the skill is between the models and between upper elevation and lower elevation sites. So first, we use absolute thresholds to measure our skill scores. In this case, it's the hit rate. These are just a threshold that we define for what is an event and what is not an event. And for example, 1.14 here would be considered the minimum value of an event, or the minimum size of an event. So this is the easiest way to start. We've got our HER-V2 line in red and HER-V3 line in green, or in blue. And we're measuring hit rate, which is the ratio of hits to all observed events. And specifically, we want this number to be high. So in this case, the version 3, the newer version of the HER is higher than the version 2 for both lower elevation and upper elevation sites. We can also look at the false alarm ratio. This is the ratio of false alarms to all forecast events. And we want this number to be lower if the model is more skillful with, in regards to false alarms. So we see that the version 2 is smaller, it has a lower false alarm ratio than the version 3 for most absolute thresholds, although for lower elevation sites this is different for the smallest events. And finally, we look at the equitable threat score. This is a skill score relative to a random forecast, which would have a ETS of 0. So this is sort of our measurement of general model skill. And I've also put confidence intervals, 95% confidence intervals, to understand the significance of the differences. And we see that overall, the models are not very different from one another with regards to ETS as a function of absolute threshold. However, by measuring with absolute threshold, we're giving each model the same, we're measuring it against the same climatology. And in reality, we just saw that the models had different biases, although slightly different. Their climatologies are different, and they're also different from the climatology of observations. So in order to remove that effect in our skill scores, we evaluate model bias not against absolute threshold, but against percentile thresholds. So for example, 75th percentile events are events that were larger than 75% of all events in the period. So to start, we go back to hit rate, and we see that both the HER version 3 and the HER version 2 are almost indistinguishable from one another with regards to hit rate for all from 75 to 95% thresholds at both lower elevation and upper elevation sites. Similar result with the false alarm ratio, although the HER V3 tends to be slightly smaller, it's both models are very close to one another. And ultimately, the ETSs are also quite similar from one another, and we would not reject the hypothesis that the models are essentially equivalent with a risk of 5% because they both fall within these 95% intervals. So to sum it all together, the HER V2 and HER V3 evaluation of bias and skill showed that both models compared together are not substantially different from one another. And in some places, not statistically discernible differences with regards to skill scores and the equitable threat score once the effects of bias are removed. And then on average, when we're talking about bias, there's a slight wet bias of the models at ASOS sites and close to neutral bias at SNOTEL sites, at our upper elevation sites. So next, we move on to part 2 of 3 in our results section, comparing the version 14 and 15.0 of the GFS together with the HRES. And because these are run globally and over longer lead times, we're able to look at both day 1 and day 3 forecasts. So to start, we're going to look once again at bias ratios, but this time we're looking just at the GFS V14, and we're comparing its day 1 and day 3 forecasts on the left and the right respectively, starting at lower elevation ASOS sites. So we see, to start, quite a wet bias at 1.65 at its day 1 lead times, and a slightly lower bias, 1.57 in its longer day 3 lead time. And also a substantial threat, even larger than what we saw with the HER V2 and V3. Looking at so looking at its successor, the version 15.0, We see a similar pattern, although a slightly larger average bias at lower elevation ASOS sites, and also a large spread from site to site in these bias ratios. Finally, we look at the HRES, day 1 and day 3, and we see even slightly larger bias ratios, and again, a large spread. So altogether, biases generally increase from GFS V14 to 15.0 to HRES, although all of these biases are quite wet. And we also see a large bias regardless of model type among or measuring against ASOS sites. Next, we look at the SNOTEL evaluation. These tend to be very close to neutral. This is the GFS V14, day 1 and day 3. Essentially neutral, much lower spread, although slightly larger than what we saw in the version 2, version 3 evaluation of bias. We see something similar in the GFS V15, its successors. Mean biases are also close to 1, and it's the spread from site to site is also relatively low. And finally, the HRES bias is what we would consider neutral, although slightly drier than what we saw in the GFS V14 V15.0, and the spread is even slightly lower. So altogether, biases decrease from GFS V14 and 15.0 to HRES, not by much, and the spread is small among, or for the evaluation at SNOTEL sites. Next, we look once again at the frequency biases of the 3 models. Red is the HRES, blue is the GFS V14, and black is its successor, the GFS V15.0. Let's see if I, okay. So we see that for regardless of event size that we're looking at, most events are over-predicted by all models. Perhaps slightly less so for these larger events, and more so for these smaller events. And perhaps more so in the HRES than the GFS V15.0 and 14. However, I think the takeaway is that all 3 models over-predict events, regardless of event size, at low elevation sites. And this is different at upper elevation SNOTEL sites. There's neutral prediction for small events, and sometimes, generally for day 3 forecasts, a slight under-prediction or a neutral prediction of events for larger events. So altogether, the differences are small between the models, or between the GFS versions of the GFS. There's over-predicting of event size in general at ASOS sites, and neutral or slight dry bias at SNOTEL sites, especially for small events, it's neutral. And finally, we look once again at the bivariate histograms, and we see that the accuracy is not quite. It seems a slight overprediction at the with regards to the GFS V14, both day 1 and day 3 forecasts, and a very large spread from event to event and site to site. This is very similar in its successor, the V15.0, over-prediction of events, event size, or a number of events, and a large spread. And this is also the same for the HRES evaluation using bivariate histograms. Then we can look at the SNOTEL sites. We see a good accuracy and a moderate precision from event to event. In the GFS V14, V15.0, and the HRES as well, although the HRES seems to feature a slight underprediction. And so altogether, the bivariate histograms reflect what we saw once again with the bias ratios and the frequency bias results, in that on average there's a slight overprediction and a large variability at ASOS sites, and a slight underprediction and a much smaller event-to-event variability at the upper elevation SNOTEL sites. So looking looking at the skill scores, we have the HRES in red, the GFS again in black, GFS V14 in blue, 15.0 in black. Day 3 forecasts are the solid lines. Day 1 forecasts are the dotted lines. There are a few things we can note that are sort of a pattern through this skill score evaluation. The GFS V14 hit rate is generally lowest, increasing to the 15.0, and then ultimately to the HRES. And day 3 forecasts, not surprisingly, have a lower skill score than the day 1 forecasts. This is muddled a little bit in these at the SNOTEL sites. In this case, 14 HRES and 15.0 in increasing order for mid to small events, and HRES to 14 to 15.0 for large events. Next, we look at false alarm ratios, which are the lowest for the HRES and for the day 1 forecasts, and largest in the GFS V15 for larger ASOS events at ASOS sites, and in general, not sort of oscillating between the 14 and 15.0 GFS at SNOTEL sites. But once again, we look at the ASOS or the equitable threat scores, and we see an increase from version 14 of the GFS 15.0 and HRES at both ASOS sites and upper elevation SNOTEL sites. However, what may be more interesting again would be using the percentile thresholds to remove the effects of bias in the skill score evaluation. So we start with the hit rate, looking at the range from 75 to 95 percentiles at ASOS and SNOTEL sites. And we see consistently an increase from the GFS V14, the GFS V15.0, and the HRES with regards to hit rate. Although this difference is largest for day 3 forecasts in both lower elevation ASOS sites and upper elevation SNOTEL sites. And the difference I'm referring to is the difference between the 2 versions of the GFS. The false alarm ratio is substantially lower at in the HRES for day 1 forecasts, and not very discernible at lower elevation sites between the 2 versions of the GFS. However, it does decrease from GFS V14 to 15.0 to HRES at the upper elevation SNOTEL sites for both day 1 and day 3 forecasts. And then altogether, we can look at the equitable threat scores. Once again, the highest scores are given to the HRES, then the GFS V15.0, and then its predecessor, the GFS V14. And this increase from the GFS V14 to its successor is the largest for day 3 events, and it's significantly large for day 3 events with a risk of 5%. And the increase from GFS modeling systems to the HRES is significant in general for day 1 forecasts. So altogether, while in general the GFS V15.0 skill scores are larger than its predecessor, the HRES still remains arguably the comprehensively more skillful model as evaluated by our metrics. Furthermore, skill decreased with elevation and lead time, which isn't surprising. And finally, bias decreased in strength from the HRES to the GFS V15.0 to the version 14. Although in general, probably more noteworthy is that bias was much lower, around neutral at the upper elevation sites and quite wet at the lower elevation evaluation ASOS sites. So finally, we wanted to hone in on some patterns that we saw in the data set. Specifically, we're looking at Great Basin and Cascade Sierra bias in the HER version 2 and version 3 evaluation at SNOTEL sites. We saw, well, the first reason for this is we saw a disparity between the biases at Great Basin and Cascade Sierra sites. And second of all, the orography is quite different between these two regions. And so this may have affected or contributed to this disparity. So we start with a figure that we've already seen earlier in the evaluation between the HER-V2, HER-V3 at SNOTEL sites. And this time I want to look a little bit deeper into these sites. The green sites represent Cascade Sierra ranges and the SNOTEL sites located within them. Their biases tend to vary from neutral to dry to wet from site to site. Whereas in the Great Basin sites in the red circle, most or all sites tend to be either neutral or dry. And we believe that this disparity might be able to be explained by differences between the orography at these sites. So the first thing we do is we pull those stations and we categorize them into either Great Basin sites in yellow, Cascade Range sites in green, or Sierra Nevada sites in blue. Next, we look deeper into the evolution of bias throughout the cool season. This is the mean accumulated precip at each station in each group, and we can over the course of the cool season. So this is increasing number of days. And so we start with the Great Basin. The observations are in black and the models are in blue and red for V3 and V2 respectively. And consistently from event to event, the model tends to underpredict the event size, and this so the difference between observations and modeled accumulated precip increases with every day in the cool season. And this is different at Sierra Nevada sites, which oscillate around, in this case, underpredicting events and overpredicting events, resulting in, and by just a small amount, resulting in close to neutral bias on average. And then Cascade Sierra sites, the bias varies from model to model, and in some cases from event to event, as you can see. So this tells us that there is in fact a difference. There's a systematic dry bias at Great Basin sites and something less coherent at Sierra Nevada and Cascade sites. So our first hypothesis that we can make is that the smooth orography of the models, the version 2 and version 3, results in these low biases wherever the model elevation is too low, and high biases wherever the model elevation is too high. And we can look at, we can examine whether or not this relationship is strong by comparing bias ratio on the vertical axis as a function of model elevation error in the version 2 and version 3 of the HER. And model elevation error is just the difference between the elevation in the model and the true elevation at each site. And so what we would expect if our hypothesis, if we could further investigate our hypothesis, is that there is a strong relationship, a positive relationship between model elevation error and bias ratio. However, that's not what we see. While Great Basin sites are indeed generally drier and the bias varies from Cascade Sierra, which are in blue, quite a bit regardless of the model, the trend is not apparent. So the next thing that I wanted to look at was how, what are the differences from region to region in the over-prediction or under-prediction of event size. So for that, I'm looking again at frequency bias. It's a plot that we've seen before. However, now I'm looking at Great Basin sites, which are in yellow, and Cascade Sierra sites, which are in blue. And the version 2 and version 3 of the HER are denoted by dashed or solid lines. And we see that for in both regions, there's a pretty consistent evolution of bias as a function of event size. And there's a dry bias for small events. We can also see that these small events tend to contribute a lot more to Great Basin precipitation than they do to the Cascade Sierra precipitation. So my second idea was that perhaps the low frequency bias for small events is related to the dry bias at Great Basin sites, just because these small events contribute more to Great Basin precipitation. Once again, we look at the correlation between bias ratio on the vertical axis and the contribution of these small events to the total precipitation at Cascade Sierra sites in blue and Great Basin sites in yellow. So what I'm looking for is a stronger correlation between the contribution of events and bias ratio. And while I found a great way to cluster Cascade Sierra and Great Basin sites, I don't see the relationship that I'm looking for, and no evidence to argue my hypothesis and to continue investigating at this point. So we come together at looking at this disparity between the biases and understanding that at this point we couldn't attribute this disparity to either terrain smoothing in the model or to a systematic dry bias for small events. So all together, we can put all our findings together. We covered number 3. The first observation that we can make from this evaluation is that the difference between the HER V2 and V3 with regards to bias and skill score are not substantially different by our evaluation. However, the skill scores in the GFSV 15.0 and the GFSV 14 are substantially and sometimes significantly different. And this is good news for the new GFSV 15.0. However, the HRS seems to be the comprehensively more skillful model as evaluated by our metrics. So this concludes my evaluation of these models. And I just want to end very quickly just by acknowledging my committee for supporting me while going through each step of the evaluation over the last many months, to the Steenberg group for helping me prepare and also work on the methods and the data section, classmates, and the University of Utah, and of course my parents and my family, some of which are here. So I'll end it there, and I'll leave this up for questions.
All right, we'll start with a couple questions from the committee. Court and John.
Yeah, nice presentation. So it's always these kind of model validations when the model changes. You know, it's a glass half empty, glass half full kind of situation. So going into this, they made a whole bunch of laundry list changes to the model. Was there anything in there a priori that would suggest that it would get better? Or is it just a better answer that it didn't get worse? When you went into this, when you and Jim sat down and talked about this, what was your sort of hypothesis as far as how the model changes were going to impact the performance?
I guess initially looking, well, first of all at the HER version 2, version 3, because these are the ones that haven't changed very much in both respects. The major improvements were the ones that I showed, the improvement in the vertical coordinate system and the improvement in the PBL scheme. My first thought was there wouldn't really be much of a change, just because I figured that the orography was a little bit more important and the model resolution was a little bit more important. And we saw that in some previous studies. For example, Tom's study, that was sort of the major or one of the major drivers of model skill and sometimes bias. So that was my original thought, was maybe it wouldn't change too much. I guess it is, I'm sure they'll be happy that it didn't decrease in skill from B2 to B3. And the GFS, I expected the skill to increase for sure. The dynamical core is such a major part of the model and it platform for all of the dynamics that occur in the model, and so I expected at least the skill to increase for sure, just for that reason.
Get away with one more. So
Yeah.
Now statistics and sample. Can you go back to your first bivariate histogram, just so I get a sense of this? So I mean, it's the roll of the dice. You do a study when precip is 40% less than normal, and so you're dealing with a finite sample to start with, and then you're dealing with unusually sort of dry events. You've kind of obscured how your presentation a little bit by using the log scale of frequency of occurrence. So when it gets, is this the frequency of occurrence per station? So when it gets to that dark color where it's 1, which it would mean the 10 to the 0.
10 to 0.
Yeah, 10
Right.
to 0. So that's 1. So is that one event at a station, or is that one event of all of these?
Oh, okay.
Because later you were more clear about it when you were dealing with the cascades, and so then I kind of wondered whether that was the situation. But 80% of your observations are in those, or well, not 80, but it sounds like 60% of your observations are in those 2 squares down there, 0, 0 kind of values, right?
Yep.
So there isn't a whole heck of a lot of data in that whole rest of that histogram. Is that a fair assessment? Can you put quantitative how many events go into like the middle of that diagram, something like that? You just have a sense of it?
So what the difference is between values far
Well,
away
just-
from the.
Yeah, I mean, just what one of those light pink colors actually means in terms of anywhere is in here. I mean, the other way to describe it is you stopped doing the blue and the green dots when your sampling got below something. So what was that threshold when you stopped doing stuff?
Okay, right. So, well, first of all, the dots are shown for samples that are larger than 100. So that would mean that 100 samples were put into this line
In that
for the
whole
blue.
line?
Yeah.
Okay, yeah, so it is
Because-
a pretty small sample.
Right. So
Okay.
for these, yes, the sample is very, very small for these.
100
larger.
across all of the ASOS stations, not 100 at one. I mean, it can't be 100 at one station, right? So,
Right, yeah.
Okay, all right, yeah. I think that's just something you gotta fess up to, in the thesis itself.
Okay.
Okay, Marcel, kind of related to John's question, because you're working with a model update, you necessarily have a short data set, right?
Yeah.
One pool season, right?
Yeah.
90 days or something. So can you defend the claim that provides enough data to provide a useful assessment of skill advice?
I would first say that if I had option to look at more cool seasons, I think that would strengthen this a lot more and make it the case that I'm making a lot stronger than it is, especially for at the ASOS sites, which I admittedly was worried throughout the evaluation that especially larger events would be undersampled just because it was one cool season. Some of these sites depend on one or two large events. However, the SNOTEL data set, again, I would prefer to have more cool seasons to work with. However, each station has 120 events to work with. Many of these stations receive events very often during the cool season. It was a dry cool season, but still received many events. So I'd be confident to say that while the results might change from season to season, that the broad takeaway that SNOTEL sites, at SNOTEL sites, these models are have a neutral bias, or that the skill score didn't change very much. I would be much more confident, especially at the SNOTEL sites, to say that that wouldn't change too much, just given the sample of events that we have at revelation sites.
And can you explicitly articulate the assumption that's required for these results to be right?
Let's see. So the assumption that is made in order to say that
like most of the analysis
for this cool season, the results are reliable. The assumption that is made is that the number of events, the sample of events that we have among the sample of stations that we have is sufficient to establish general model bias for season to season.
How about questions from the audience?
Like I got a fair bit done this morning.
Peter?
They're gonna ask me about
So
that.
you and I had
gotta
discussed
get
this a little
going.
bit, Marcel, but how did you end up dealing with the fact that during snow events, especially if you have cold temperatures and/or high precip rates, that you get the buildup of snow in a gauge orifice that doesn't actually fall in, and that would be a situation where I guess the precip would be under-reported by this site. Right? Did you deal with that at all?
I didn't deal with that. I would have liked to have dealt with it. Although I did. So you had a sort of quality control sort of algorithm that I used for some of the data that I put in, and it changed the results slightly. So I think it would have had an effect. I don't know if the effect would have been drastic in order to change the general findings, but I would have preferred to have used, for example, your algorithm, but I didn't account for that.
Because another kind of simple way to do it too that could be useful is just breaking out rain versus snow events, setting say like 40 Fahrenheit or whatever, because obviously the rain events aren't going to have that, and you can see how your results change. That's
Okay.
No, I was sipping tequila by myself.
Yeah, if you jump to slide 58, where you're talking about the Cascade and Great Basin differences. So, kind of in general, it seems like the takeaway was with the HER that there was a neutral bias ratio overall across the western U.S. Actually, maybe not this one. Jump. Yeah, keep going. Might be 68. Yeah, okay, so go back a slide. So in your figure C, the Cascades, where it flipped essentially from the HER V2 being low bias to SNOTEL and the HER V3 being high bias to SNOTEL. So there's 2 points to make here. One is, can we really attribute some of these biases to the terrain being too low for the real observation or too high for the real observation, like you assert, if I assume the terrain in each of the Herbie 2 and Herbie 3 was consistent, or did they make some major changes there?
Right, so the orography is the same between the models.
Right. So I guess what I get at overall is just, can we really can we assume that a lot of that is due to the orography if there's clearly something else dynamically or physically that is going on that flipped that bias?
Right, so the cascade biases specifically, I'm not sure what the difference is between the models, what caused this difference in the models. And I wouldn't say that it is because of, or that I would think that it's because of the orography. But to me, what's meaningful is the difference, is the comparison between Great Basin sites, which are consistently dry in both the version 2 and version 3, despite very small differences, or relatively small differences. And the cascades and the behavior, although it's different from model to model, is less systematic. And so there is a difference just in that way.
And then I guess to just tag off that point, the second thought that I had was, even though overall the biases are neutral in the HER, are there regions where those biases are significant and non-neutral? Right. Are there certain regions that are consistently high or low biased?
Oh, okay. I looked into that a little bit. Of course, obviously the areas that I looked into, there was an area. So in the HER version 2, which Tom's evaluation also saw, was dry bias in general in here. Among the ASOS sites, I won't jump into it, go all the way, but I mean, most of the sites were very wet, particularly wet were the Intermountain West, or specifically the Colorado Rockies. Although ASOS sites tended to be just generally wet across the board.
So this might just be a bit of confusion on my part about the model development process, but the new version of the GFS was in development during this time period. How do you know they didn't make a change to it in the middle of the season that might have affected how it performs?
That's a really good question. So I mentioned, I didn't mention this, but this is a great time to mention. So I've been using the version 15.0, which is not the operational version. The operational version is 15.1. You might have seen that there was an issue with the total snowfall over the course of the cool season that a lot of meteorologists were worried about, and model developers. So there was a bias in there that they've corrected for but not completely solved. We talked to Alicia Bentley at the Modeling Center, and they've tested a little bit. She said that the snow water, or the liquid water content would not have changed, would not have made a difference between the results for the version 15.0 and the 15.1. So based on that, I'm confident that the evaluation of 15.0 is at least similar to the evaluation of 15.1, and that the takeaways should be the same. But that's a good question. Yes?
Yeah. Do you have any insights as to why the models universally do better at the high elevation sites as opposed to the others?
In terms of like skill, or?
Yeah.
Well, actually, I would say that the upper elevation sites, the models do worse capturing events, but in terms of bias, right, and bias, that was, yeah, that's also something that I thought about. I guess the better figure to look at would be, let's just say this one. So, or actually, I like the comparison between SNOTEL and ASOS. So, at ASOS sites, well, for one, I think a course resolution model should should be slightly wet, just because it isn't resolving terrain very well. Although it does better at the SNOTEL sites, and there's a few. So I'll say the first reason, perhaps, that the SNOTEL sites should be qualified by the measurement error that I mentioned earlier, which is the undercatch. I don't know how big of an effect the undercatch of precipitation would have, but the bias would increase if that effect was taken out. Sorry, it would, yeah. And so the next thing is that events at ASOS sites are, one, temporally sporadic. So they're, I think, at least during the cool season, somewhat unpredictable. And so, you know, if you miss one or two of these events, then from site to site, you can lose, or you can perform pretty not so well. Whereas at the SNOTEL sites, these events tend to happen or not happen, and so if they capture them, then the bias tends to be closer to neutral.
I'll take a stab at that.
Yeah.
The reason why you have a wet bias in the valleys and a neutral bias in the mountains is because the models overall are too wet. Okay? You get a higher equitable threat scores in the valley because the biases are really high. Models that produce lots of precipitation generally produce higher equitable threat scores, suggesting that there's greater skill, but the equitable threat score is an imperfect measure, and that often happens a lot. So models, if you want to, equitable threat score is the measure you use for your model, you turn it up a little bit to make it produce more precipitation. That will make it look better with these old metrics. We need to come up with some better ways to deal with this. So, all right, with that, let's give Marcel one more hand. The audience is now dismissed, and the committee will talk to Marcel.
2 days, huh?